We're continuing our discussion of determining the masses of stars problem. Remember, in part A, we looked at the frequency shifts for the light produced by heated hydrogen gas and compared it to the value at the laboratory to find the speed of the motion of the system of binary stars and orbital speeds of the stars. And our conclusion was that the system is approaching the Earth. In part B, the light from each star in the binary system varies from its maximum frequency to its minimum frequency and back again in a period of 11 days. Determine the orbital radius capital R and the mass m of each star. Give your answer for m in kilograms as a multiple of the mass of the Sun, 1.99 10 to 30 kilograms. Compare the value of capital R to the distance from the Earth to the Sun, 1.510 to 11 meters. This technique is actually used in astronomy to determine the masses of stars. In practice, the problem is more complicated because the two stars in a binary system are usually not identical, the orbits are usually not circular, and the plane of the orbits is usually tilted with respect to the line of sight from the Earth. Okay, so we're measuring the period of the circular motion for these stars from the lab reference frame. And you know, when the source is approaching, we have a speed v minus v center of mass, and when the source is moving away, we have a speed v plus v center of mass. And we have found that the maximum frequency will occur when the source is approaching, and the minimum frequency will occur when the source is moving away from the observer. So that means we have maximum frequency, minimum frequency, and maximum frequency again. That means we complete one full cycle. Okay, so in part B of this problem, we have a measurement of the period of the circular orbit. The period measured in the laboratory reference frame, in S frame, which is the Earth reference frame, was reported to be 11 days. Now, if we want to measure the period of revolution, one full revolution, the proper reference frame to do this is the reference frame of the stars. Why is that? Because the measurement starts at the same position in space as it ends for an observer on one of these stars. So I can say that the proper time for an event is measured in the binary star center of mass reference frame, because the center of mass doesn't change. We have an observer sitting in the center of mass reference frame, looking at the same position in space with respect to the center of mass and noting the passage of a binary star. So we have a report of this star passing according to the center of mass observer, and then it comes down and goes back again, and it's passing again the same location. Therefore, the center of mass reference frame would be measuring the proper time. Okay, so center of mass reference frame S0 measures the proper time. So the time measured by the Earth reference frame is dilated. It's the relativistic correction factor gamma times T0. Therefore, the proper time would be the time measured in the Earth reference frame divided by gamma. So that's the first thing I want to note. Now in the S frame, the Earth reference frame, I know v, the orbital speed of these stars, and it's going to be equal to 2 pi r, the circumference of the circle, divided by the period t. So I can say that the radius would be given by v times the period divided by 2 pi. So this is all in the S reference frame. So all these values reported in the S reference frame. So if I calculate this, because I know the orbital speed from part A, 3.94 10 to 4 meters per second, the radius of the orbit is 3.94 times 10 to 4 meters per second. The period is 11 days. One day has 24 hours. 1 hour has 60 minutes. 1 minute has 60 seconds. So convert to seconds. Divided by 2 pi. And that gives me, for the radius of the orbit, 5.96 times 10 to 9 meters. And I'm supposed to compare it to the distance between Earth and the Sun. Earth-Sun distance is 1.5 times 10 to 11 meters. So I can see that this capital R is 0.04 times Earth to Sun distance. Okay. Now, why do we have this uniform circular motion? Because we have the centripetal force. So I can note that the centripetal force, which keeps the trajectory of the binary star along this circular orbit, is the gravitational force between them. So I need to account for the centripetal force by considering the gravitational force between them. Now these two stars have exactly the same mass, and they're at a distance 2r each other, and gravitational force is an attractive force. It will point towards the center for each star. So I can write the gravitational force, which is universal gravitational constant g, the product of the masses, m square, divided by the distance between them, 2 capital R square, is equal to mass times the centripetal acceleration, m v square, divided by capital R. And you can see here one of the masses will disappear. So this will give me, for mass of one star, 4 v square capital R, 4 v square capital R, divided by the gravitational constant g. So that's how I can calculate the masses of the stars. So if I plug in the numbers, I have 4 times the orbital speed squared, 3.94 times 10 to 4 squared. The radius I just calculated, 5.96 10 to 9 meters, divided by the universal gravitational constant. If I look up its value, it is 6.672 times 10 to minus 11. So this gives me a value for the mass of one of these stars to be 5.55 times 10 to 29 kilograms. And I'm supposed to compare it to the mass of the sun. And mass of the sun is known to be 1.99 10 to 30 kilograms. So I find that the mass of one of these stars is 0.279 times the mass of the sun. Okay. And finally, I want to make a remark here. So we can note that the speeds we calculated, the orbital speed and the center of mass speed, v center of mass, turned out to be much less than the speed of light. So the center of mass was 13.1 10 to 4 meters per second. The orbital speed is 3.94 10 to 4 meters per second. They are both much less than 3 times 10 to 8 meters per second. So what's the conclusion? So we could have, in this problem, we could have used the non-relativistic Doppler shift formulas. And just as a reminder, in the non-relativistic case, the maximum frequency would be measured for the source approaching the observer. It would be f0 times c divided by c minus u. And the minimum frequency would be for the source moving away from the observer, c divided by c plus u, where u would be v plus or minus v center of mass, depending on which scenario we're looking at. So this is for the case source approaching, and this is for the case source moving away. Okay, so if I calculate the shift in the frequency, f minus f0, this would be f0 times c divided by c minus or plus u minus 1, which is f0 times c minus c plus or minus u divided by c minus plus u. And we can see the c's will cancel here. And if the speed is much less than the speed of light, u is much less than the speed of light, this can be neglected as well compared to c, because u is much less than c. Then we would find an approximate expression for the frequency shift to be plus or minus f0 u divided by c. So this is our non-relativistic Doppler shift. Okay, so just to note here, this is an acceptable approach as well, because we do have this condition being satisfied in this problem. Okay, so we talked about the binary star system, two masses, identical masses m, moving with the same tangential speed v in a circular orbit around the center of mass, and the system is being observed by an observer on Earth. We're looking at the light coming out of these sources, and in one case, the source is approaching the observer. In the other case, source is moving away from the observer. When the source is approaching, we can use the relativistic Doppler shifts formulas. Source is moving toward the observer, it's f0 square root c plus u over f is square root c minus u, and moving away, square root c minus u over square root c plus u. So I calculated the maximum frequency for the source approaching the observer with speed v, the orbital speed v minus the center of mass speed. I can use this formula, and with that I can calculate the maximum frequency. And for source moving away, I can use v plus v center of mass as the speed of the object, and that's going to be inserted into the relativistic Doppler shift. And by looking at these, the sum of the v minus v center of mass and v plus v center of mass written in terms of the Doppler shift equations, I can obtain the orbital speed. And once I obtain the orbital speed, I can plug it into any of these equations to find the center of mass speed. And it turns out to be negative, implying that even though my convention was that the system of the binary stars was going away from the observer, it turns out that it's actually approaching. So this is a minus sign. In part B, we looked at the period of one full revolution in the S frame, and the rate it's going to be equal to the measured speed v, which is equal to 2 pi r divided by the period. So I can calculate the radius of the orbit from this, and the centripetal force is the gravitational force that pulls these two objects together, and that's equal to mass times centripetal acceleration. From that I can calculate the mass and compare it to the mass of the sun. And finally, if I were to use the non-relativistic Doppler shift formulas for the scenario stationary observer source approaching and stationary observer source moving away, I have these two results. So I could look at the shift in the frequency compared to the frequency measured in the proper reference frame. I can find the following non-relativistic Doppler shift formulas, and I could use this to calculate the center of mass speed and also the orbital speed of these stars.